Everybody, Mr. Smith here, and in today's lesson, we are going to investigate reflections of functions. So some of this may be a bit of review and seem like an extension of the grade 10 course when you transform quadratic functions, but some will be new, specific to the 3U course. So let's get started. So as has been our habit, we are going to start by looking at a group of functions. And so in this first group, excuse me. Ooh, okay. We have our original function is a radical function. And we're going to sketch three other guys. So the square root x, and then we're going to put a minus in front of the square root. We're going to put a minus on the x inside the square root, and then we're going to do both. And we'll see how these graphs look different. And then see if we can come to any conclusions based on what we see. So I've got handy dandy Desmos open here, and let's these guys to go. I guess you can just type the actual expression. And y equals, so negative square root of x. I want to be clear, hopefully, that you are pausing and trying these on your own. You can always just follow along with me too. Negative square root of negative x. So we get this cool pattern happening here. So in blue, with the negative out front, we got it kind of opening downwards like so. In green, where the negative was on the x, we have it actually going back into the left. And then with the two negatives back to the left and kind of opening down. So let's just get these down. Some different colors here. So this guy was down here. So right now I have I have like a night light filter on my computer to minimize just because I'm staring at my screen like all day long at school, teaching 2 classes and prepping at night, just to help a little bit. So see, that looks pink to me, but I'm not sure what it looks like to you if I had the normal colors, but it's all good. I'm just using different colors here. And we'll use whatever this guy is. I think it's different. Can't really tell if it's too much different, but anyway, that's okay. All right, there we go. So, just observing what happened, there definitely wasn't a translation. There definitely wasn't a stretch. Something else has gone on here. Spoiler alert, title of the note. So think if you can describe what happened there in terms of reflections. So start just formulating maybe a rule in your mind. We're just going to do one more and see if maybe the rule, maybe you think you know what will happen with the negative up front. Maybe you think you'll know what will happen with the negative inside on the x. But let's kind of see with this next group. So here we're transforming the basic parabola, y equals x squared. And let's head to Desmos and see what happens. Again, it'd be great if you paused it and just tried these 4 on your own. But you can always follow along with me. Okay. And then negative x squared. So that's probably, from your grade 10 course, that's probably what you expected to see. That's just the standard parabola is opening down. But what would it look like if we did the negative x and then squared? So do you see? We actually don't get anything new. It's actually equivalent to the first function, which makes sense, right? Because negative x times negative x is positive x squared. And finally, the negative of negative x squared. Didn't give us anything new either, but that kind of makes sense, right? Because negative x times negative x is x squared. And then when you stick a negative out front of that, is it not just like the second one? So you can kind of see how those are algebraically equivalent, but they do follow the same rule that the first group of functions did in terms of reflections. So let's get these down on our page in your note there. So we got the original, negative x squared is down, and then h at x we actually saw was the same thing. So however you can kind of do that on your sheet, using different colors makes it actually really helpful to see they're the same and you can kind of differentiate. And I guess we'll use that guy. Well, that's too similar. Let's use this dude going down. And that was j at x. Okay, let's talk about these things in terms of reflections. Let's look at the 2g of x's. How would you describe the transformation from the original to these guys g that I have opening in green, I guess, in both cases? In terms of the, if you look at the note and just recognize, okay, they're a reflection in what? So we would say that those first two cases, change my font size a bit lower here, where the negative was out front, we got a reflection in the x-axis. So if you think about it, all the points that were above the x-axis got flipped to below, or below they get flipped to up. So we say it's a reflection in the x-axis. Sometimes you say that's like a vertical reflection, reflecting this way, but technically we say it's a reflection in the x-axis. And I want to add something as well. I want to mention, I might make a bit different font. I want to say that's about how the points are mapped. The point xy, or the point xy, so some general point on the original, is mapped to, and if we think about what happens if it's reflected in the x-axis. So if it's reflected down, its x position's not changing, but it's, it gets reflected to the negative side, or if it was negative, it goes back to positive. So it's the x value becomes the opposite sign. So this is what it looks like. The point xy is mapped to x negative y. Its y value changes sign, which allows it to flip vertically. For the case where we had the h of x's, when we had the negative on the x, so look what that did. It reflected it horizontally from the right side to the left side. All the x values change sign, but the y values change the same. This is true for the on the bottom too. It's just that the basic parabola y equals x squared, you'll notice it's symmetric, right, about the x-axis. So if you flip things around, you get the same graph. So that's why we got the same graph. So let's add a little note there. So this guy is a reflection in the y-axis. And we'll make a note about how the points are mapped. The point xy, so some general point, is mapped to, it's the x that changes sign and its y value stays the same. Finally, what happened with the last one, j? Well, it got flipped vertically, and then that vertically flipped one got flipped horizontally. It got flipped twice. And that happened with the second one as well. It got flipped down to the function g opening down, but then that's symmetric too. So when you flip that one, it looks the same on either side. But in general, when you have a negative out front of the function and on the x, what this is a reflection in both axes. And in this case, a point xy is mapped, well, both reflections happen, right? So it's mapped to negative x and negative y. Those points just change signs. So probably a little bit of an easier transformation to wrap your mind around. We don't have to do too many more examples. We kind of see the idea. So this will be a bit of a possibly shorter note than the previous two were. Let's put this into practice a little bit. So I've asked you guys to sketch the function root x plus 2. So we should be able to do this fairly quickly and efficiently. And maybe you can do it. Maybe it takes you, maybe you want to draw, maybe you want to do it this way. At this point, we should all recognize the base function is the square root function. And at this point, we should know that those base points are 0, 0, 1, 1, 4, 2, and 9, 3. So that's the base function, root x. And then, of course, root x plus 2, we know now that that is a vertical translation up 2 units. The 2 is outside the square root. So if you shift every point up 2 units, you get this. So this is the graph of our function f at x equals root x plus 2. And then for all the later graphs, you can just copy that one down as well. I might actually just do that while I'm thinking about it. Maybe you want to as well. 4, 4, 9, 5. That is f at x equals root x plus 2. And I think we had one more example. Yes, we do. And 9, 5. Something like so. Get those added in. All right, and now we're ready to go. So in this exercise, it's just I'm getting you guys practice. One, just like applying a reflection. But two, actually seeing what the equation might look like. So what would the equation look like if we took f at x and we took that and we reflected it in the y-axis? So first of all, can you guys draw what this would look like? If you reflect this, to me it looks pink, but if you could reflect that guy in the y-axis, what would that graph look like? If you want to take a moment and try that, you can go for it and unpause when you're ready. I'm going to go ahead. So all the y values get flipped, right? So 0, 2 goes to 0, negative 2. Everything gets, in the y-axis. Yikes. Good thing I caught that. So we're reflecting in the y-axis. So imagine like a little mirror on the y-axis and reflect everything through. So 1, 3 would go to negative 1, 3. And it kind of has the same shape. It's just reflected. Negative or 4, 4 goes to negative 4, 4. And then our last point, 9, 5 goes to negative 9, 5. And so the graph of this function h of x, that is a reflection in the y-axis, would look like that. Just some notes. So let's just talk about where some of the points went to. So the point 0, 2, what did it get mapped to? Well, it was invariant, right? Because it was on the y-axis. So if you reflect that in the y-axis, it's not going to move. Now let's just do a couple more points. So we had the point 1, 3. Where did it get moved to? Minus 1, 3. Remember, for a reflection in the y-axis, it's the x value that changes sign, right? And then one more, the point, let's just do the point 4, 4. It got mapped to negative 4, 4. And we've sketched it. Let's talk about the equation. So a reflection in the y-axis looks like this. H at x is equal to f at negative x. That's how we described, zoom in a little bit here. That's how we described a horizontal reflection or reflection in the y-axis from earlier. And now we actually know what that function is. F of x is root x plus 2. So let's replace the x with negative x. So this is equivalent to the root of negative x plus 2. And you know what? Since I've got Desmos open here, I can actually pretty easily just check these guys. Definitely advise you guys to make use of Desmos too. So there's the base function. And then our starting point was root x plus 2. So that's our starting point. We graph that guy. And then let's just see if our equation works. Root of negative x plus 2. Yeah, it gives us that vertical reflection in the y-axis. So we know we have the equation right too. Finally, let's talk about the domain and range. So the domain for this function, so you can see from the graph, the domain is x can be any real number, but x has to be negative or 0, which makes sense because to square root you have to square root a positive or 0. And so we can only put in negative values for x, so that negative makes them positive. In the range, we can see the y values only hit values above 2, above or equal to 2. All right, so that's our first one. Let's do the second one. So as we did in the previous one, can you guys reflect this guy in the x-axis? Can you describe where the following 3 points get mapped to? Can you maybe find the equation? That might be a bit challenging. I'll do it with you guys. But if you have the graphs, you could probably do the domain and range as well. So I'll give you, you guys should pause the video. You can try that, unpause when you're ready. So I will assume you've tried that if you want. I'm going to continue. So if we reflect in the x-axis, it looks like this. We're kind of symmetric about the x-axis. So 0, -2, 1, -3, 4, -4, 9, -5. So it's like it's mirror image on the other side of the x-axis. We're calling that r at x. 0, 2 went to 0, -2. 1, 3 went to 1, -3. 4, 4 went to 4, -4. It's the y values that changed, right? And we know this from our rules from earlier. The graph of a reflection in the x-axis, the point xy is mapped to the point x minus y. The y values change. And in this example here, guys, all those y values were positive and they became negative. But if the y values were negative, when you flip them, they would become positive, right? Let's talk about the domain and range while we have the graphs. We can see that the domain, x has to be greater than or equal to 0. And for the range, the y values are less than or equal to -2. Those are the only y values that come out. What would this equation look like? So this function r is a reflection in the x-axis of the function, the original f of x. So minus f of x. That's how we describe a reflection in the x-axis. Now we know what f of x is equal to. It is equal to root x plus 2. So that's actually the equation for r, but we're going to write that as negative root x minus 2. So this is just a cool talking point. So if you look at this final equation, we can tie in some of our earlier material on translations, because the first part of this function, negative root x, means you take the basic root function and you flip it, and the minus 2 on the end means you move that down. And maybe I can show you guys that with Desmos. So if we had negative square root x, like that, and then negative square root x and minus 2, you can see we get the graph that we had. And yeah, it's a combination of a reflection and then a translation, which is pretty cool. Our next actual lesson is on combining transformations together. But that's for another lesson. We're just focusing on reflections right now. But yeah, that's another example of actually coming up with the equation of this function. Let us continue with one more. So now we're going to reflect in both. So if you guys want to try graphing what that looks like, stating how those 3 points we've been using get transformed, where are they mapped to? 1, 3, and 4, 4. You can pause the video and unpause when you've had a try. I'll assume you've done that and we'll move forward. All right here. So remember, when we reflect in both axes, we change both the x value and the y value. 0 won't change signs, but we'll have minus 2. 1, 3 will go to minus 1, minus 3. And 4, 4 will go to minus 4, minus 4. Reflected and reflected again. Negative 4, negative 4. And then that final point would go down at negative 5 and then negative 5 for the y value. And it would look something like this. We're calling this S of x. From the graph, we can see the domain. In this case, we only hit the negative x values and 0. And for the range, we hit y values less than or equal to negative 2, below negative 2. Now, what's this equation look like? So a reflection in both axes, we described it this way. We have a reflection in the x-axis and a reflection in the y-axis. Now, if you recall, we already did f at negative x, right? We have that up here. It's negative x plus 2. So I'm just going to make use of that and just plug that in. Negative of the root of negative x plus 2. And then distributing my negative, I get the negative of negative root x minus 2. Which actually makes sense if we think about it, because the negative of negative root x indicates we're reflecting the basic square root function vertically and horizontally. I'll just show you. Just check this out. Negative square root. We've already seen this one. But yeah, there's that double reflection of the square root function. And then if we look at our sheet, it's just that lowered by 2, right? So if I copy the above one, x, and then just lower it by 2. Yeah, I mean, we did it right. We did awesome. So that's just a little exercise in tying a lot of things together, finding equations, talking about where points get mapped to, being able to apply some reflections. So in this final exercise, this will actually be pretty quick. Can you describe the reflection that transforms the original function I have in a bold line, a solid line, into the function that's outlined with a dashed line? So if you want to take a moment and think about that and unpause when you're ready, you can do that. So I definitely encourage you to give it a try on your own. Don't just keep watching the video and just copy down what I do just to get done as quickly as you can. We want you to come across these things naturally, try things, get practice in, so you get better, right? You just don't get better copying down things that I write down. All right, so if you said that something like this, g at x is f at x reflected in the x-axis, good for you. That's the only reflection going on here. And we could write that equation. We could write it like this. G at x equals negative f at x. Because look, the points that were above get flipped to below. The points that were below, their y values are negative, they get flipped to have positive y values. And in the second case, hopefully you said this is a reflection in both. G at x is f at x reflected in both axes. And we would write that g at x equals the negative of f at negative x. Right, this function is kind of rough. I might even just be more careful. Just get some couple accurate points here. There, and there. So it's reflected in the x-axis, reflected in the y-axis. And maybe just one quick talking point before you go. You know, think when we did translations, we talked about how it doesn't matter whether you shift something left or right, then up or down, it doesn't matter. Excuse me. It is the same with reflections. it doesn't matter whether you do the vertical reflection first and then the horizontal one, because as you can see, if I reflected this guy over here instead, the vertex would be here, here, and here, and then I reflected this one vertically, I get the same result, right? So the order of reflections doesn't matter. So that's just something to keep in the back of your mind, especially later when we do combinations of functions where we're translating left and right and up and down, we're stretching, maybe both vertically and maybe horizontally, and in addition to reflecting. So we're going to do some functions that have maybe all of those going on. But until then, here's just some suggested practice for you guys. This may be tweaked when I work with you guys actually within the class. But it's never a bad idea to look at those key concepts. And then I may add to or take away from those practice questions. Hope you enjoyed that lesson, guys. I certainly enjoyed delivering it. Hope you're having a great day. Stay well. We'll see you soon.